All right. So we have done 2 lectures, and I just want to briefly recap what we have covered. So essentially, this course is called Large Sample Theory. And in many contexts, you will see people just refer to this as asymptotics. And we have been using this word again and again. And what it essentially means is that we are studying the behavior of statistics when n, the sample size, is large. That's it. So therefore, the statistics we study, right? So usually we refer to that as theta hat n, which is an estimator of a true parameter theta, estimates theta. And this theta hat n itself is just some function of our sample. And our sample, we can refer to them as x1 to xn of size n. So in a very typical setting, we refer to n data points collected in some way as n observations from some population. But there are some tricky things, for example, whether we can assume the n observations to be independent or something like that. And so there are some tricky things to think about, but this is the general setup. So essentially, asymptotics is a way to study the behavior of theta hat n as n gets large. And so the mathematical framework we use for this study is this large sample theory. And in particular, in the old days, like I said, without computers, it's very difficult to do anything that is not in closed form. So therefore, the asymptotics or large sample theory is usually concerning about the distribution of theta hat m. So here the question is, what distribution does it follow? Can we get some nice closed form for the distribution? Then if that's the case, then it will make computation by hand possible before we had computers. Okay, but of course later, once we have computers, we can use something numerical, for example, Bootstrap, which is something we'll talk about later. Okay, but that's the big picture of this class. So as I try to cover more modern things in this year, so I will need to squeeze some of the classical materials in shorter time, right? In fewer lectures. So that's why we have been in the past 2 lectures compared to what we did in what I did in previous years. I have skipped some of the proofs of the theorems, but focused more on the results and interpretation. Okay, in the last 2 lectures, what we did is basically the following. In the first lecture, we went over the basics, mathematical foundations of the limit. We talk about asymptotic relationships such as small o, right? What does that mean? It means that if we write an as small o of bn, then it basically implies that the limit of the ratio an over bn as n goes to infinity is 0. That's what we talk about. Okay, and we also talk about the same order, okay? Sorry, same order. And before I talk about action, maybe say that it is asymptotically equivalent, something like this. So asymptotic equivalent. Let's see this first. Use the tilde sign. So here, an tilde bn, this implies that the limit of the ratio is 1. Okay, so asymptotic, they're equivalent. And same order is more relaxed than asymptotic equivalence. We use this thing. And when we write am, same order bm, this implies what? This implies actually the limit of an over bn, we'll write this again, is bounded. Okay, so essentially, or maybe I just put the absolute value here just to avoid some sign issue, but the bounds should be away from 0 and infinity. So it's bounded, we call that same order. But you can see that asymptotic equivalence implies same order naturally. So finally, by combining small o and same order, we have big O. Okay, when we write AN is big O BN, then we imply both. So it means that either AN is small o of BN or AN is same order of BN. Okay, so the reason why we introduce these relations is because we can use them for some simple arguments. That is, AN may be a quite, how to say, AN, if we write say AN small o BN, it means that the terms in AN are negligible compared to the terms in BN. Then maybe when N is large, we can just ignore AN because they don't matter that much. That's the thing. And for same order, it means that, okay, if we ignore the constant, like the ratio, maybe it's a constant somewhere between 0 and infinity. If it's just they differ by a constant, then we can use the simpler form to replace the more complex form. Then mathematically, that's simpler. But all these arguments are in relation to N. So we need to be careful regarding whether the sequences AN and BN increase as N increases, or do they decrease to 0 as N increases? So that's different directions, right? Because if AN and BN both increase as N increases, then this small o means that BN increases more, faster. Or if they both decrease down to 0, then it means that AN goes down to 0 faster. Okay, that's the most important thing in our first class, and also, of course, the review on the concept limit. What do we mean by the limit of a sequence or the limit of a function? In the second class, we talk about 4 modes of convergence. Okay, so what are they? So in this case, we are now moving away from real values. We talk about random variables or random vectors if we have more than one dimension. So in this case, if we write xn converge to x, both are random. We need to specify the mode here. In what mode do we have the convergence? And first of all, we have the convergence in law. Or some people write convergence in distribution L or D to X. So this just implies the convergence of the CDF function pointwise. So essentially we have fxn, the CDF function of xn, at any value x converge to fx, the CDF of x, at that value. But here we only consider the values x where fx is continuous at. So in other words, we can write this, C belongs to big C of fx. So this means that the continuity set of the function fx, so the values at which fx is continuous at, only for these values, we need to ensure that we have the pointwise convergence of CDF functions. So that's the definition of convergence in law. And this is what we use in central limit theorem. Central limit theorem. And also when we talk about the limiting distribution or asymptotic distribution of this statistics theta hat m, this is what we need. Convergence law. So very important. The second mode, which has stronger requirements, is called convergence improbability. Okay. So in this case, we do need to care about the simultaneous values xn and xpig. Okay, we cannot let them be independent. But for convergence in law or distribution, we can let them to be independent. We can let them be independent because we just care about their respective distributions, but not the particular values they take in one realization. But for the convergence and probability, we care about the values they have in one realization. So the definition here means that for any epsilon positive, the probability that xn minus x greater than epsilon, which we call the violation of them being close, right? This means that they are not close by epsilon standard. And this probability of having this violation will go down to 0 as n goes to infinity. That's it. So then this means regardless how small the neighborhood is, then this probability will always go down to 0. But this doesn't mean that for every realization of the sequence, it converges, because this probability is looking at every n across all realizations. So as long as the violation probability across all realized sequences is small, we don't care about individual sequences. And that's the biggest difference from almost sure convergence, which we'll talk about next. Okay, and the next one is called convergence in quadratic mean. Or the more general form is, let me say, convergence in the Rth mean. So what this means is that if we take the expectation of xn minus x, so I'm just talking about some norm of their difference. If both xn and x are vectors raised to the power r, this will converge to 0 as n goes to infinity. So the difference here is that we're not looking at the violation probability, but we're looking at the overall expectation of this violation difference raised to power r. So in other words, the idea here is we look at something on average, and we're not looking at this violation probability. So the difference here is it's possible the violation probability is small, but if the violation value, that is x and minus x absolute value difference, if this value is very large, even though it only occurs infrequently, then this thing could still explode. Okay, so that's the thing. But on the other hand, if you can control this, then we can go back to the probability. So basically, the Rth mean convergence implies convergence in probability, and this is guaranteed by the so-called Markov inequality, basically. So the idea is that if we can control the overall expectation of the Rth mean, then you can imply the probability convergence, but not the other way around. Okay? So that's what I'm saying. And also you can have convergence in probability implies convergence in distribution. That's what we said last time. Finally, there's a very strong one, convergence almost surely. So this means what? This means every realization converges. Or we can say the convergence happens with probability 1. So the limit of xn being x happens with probability 1. This is almost sure convergence. And we can also show that almost sure convergence implies convergence in probability. Okay? But these two things don't imply each other. So almost sure convergence doesn't imply Rth mean convergence or the other way around. So except the 3 arrows I draw here, other relationships don't hold in general, but they may hold with some additional conditions. Okay, so I also want to say that this Rth mean convergence is often used when we talk about the mean squared error of an estimator, right? That means how far away is our estimator from our true parameter. So it's about this property, and we often use the mean squared error. So let me just put here is expectation of this thing. Theta n hat minus theta. I'm using the L2 norm square. So this is what we talk about often. And if it's scalar, then you can just change the norm to absolute value. Right, and there's a very famous formula for this one. The mean square error can be written as the bias square plus variance. And this is something people often use to, introduce into intuition behind the so-called bias variance trade-off. That means if you have two estimators with the same mean squared error, one has larger bias, then the other must have larger variance. And also, if we want to minimize the mean square error, we have to consider both. It's possible that you can introduce some bias into the estimator, but if the variance reduction can compensate what you increase in bias square, then it's worth it. And that's what we actually did with the so-called shrinkage estimators like Lasso, where we did introduce bias, but we actually make the estimator less variable. Okay. And regarding the convergence in probability, this is actually quite useful as well. It's related to how we think about whether an estimator is called consistent. This is what we'll introduce today. A consistent estimator means the estimator theta hat m converges to the true parameter theta in probability. And that means if we have a large enough sample size, we can expect that the estimator is close to the true value theta with high probability, and that's what we're satisfied. So in other words, in statistical thinking, a lot of the conclusions we have hold if we do have high probability. If we have high probability result, then we are happy with the result. Okay. Another thing I would like to say is the almost sure convergence. So this one is not so widely used in statistics. The reason is because it's too strong. You actually require every sequence to converge. You don't accept any violations. But on the other hand, it could be a useful mathematical result if we just want to get into convergence and probability. So basically, we can use almost sure convergence as some kind of intermediate step. In particular, in last lecture, we introduced an alternative definition of almost sure convergence. That is, almost sure convergence of this, right, can be written in the form similar to the convergence and probability, but except saying, okay, just as n goes to infinity, this go down to 0, we need to have a stronger thing saying that, okay, basically for given epsilon greater than 0, there exists a k, then after that k, everything in the xm and greater or equal than k, everything of that is within the epsilon neighborhood. So we cannot just say about one particular m, but everything beyond that. So that can imply the almost sure convergence. So essentially, we want to say that, so for the almost sure convergence, it's used as a mathematical tool useful. And also for partial result, which we also said last time as a recap, is that for the convergence and probability, we can argue that some subsequence of our xm can satisfy the almost sure convergence. So that is another way to apply this result as intermediate. And okay, so last time we also talked about the Slutsky theorem and continuous mapping theorem, which are two ways to let us combine some convergence result into a result for our statistic. Because for our statistic, like theta hat m, it may be composed of different parts, right? It may be some addition, multiplication, or ratio of some other random variables. If we can show that each random variable sequence has convergence in law or in probability, then their combination can also satisfy that convergence, right? That's Slutsky. And for continuous mapping theorem, it's about the F something, right? F of xn, so basically the F is a map. So these are the quick review of our last lecture. So if you want to see more details about the proofs, we covered those in previous lectures, and you can check it out in my previous recordings if you're interested. All right, do we have any questions before we continue? Since we have a small class, then if you have any questions, please feel free to ask.
Maybe this is not covered by the class, but are there like any study in the other way around, whereas we assume that n does not go to infinity? Because, for experiment, it's sort of absurd to think that you have like infinitely many sample in an experiment.
Yeah, exactly. Good question. So more recently, people talk about this finite sample guarantee. So when people use that word or finite sample results, it means that they fix the m. Yeah, they consider that for a particular m. And there are some results people may refer to as concentration inequalities. So these are the results where we actually talk about a fixed M, where the given a fixed M, your statistics still behave in a concentrated way. It is not so far away from your true value. But in that result, typically people just talk about the rate for the, how to say, concentration. Basically, you look at how that violation probability that the statistic is far away from the mean, how that violation probability depends on your sample size n, depends on your dimension p. So in other words, you will see how that rate change with n. Then you may argue, okay, this statistics is better than the other statistics because this statistics converges or is concentrated around the true value at a faster rate in terms of n, then I prefer that. Yeah, so it's for different use. But actually for what we are talking about here, the limiting distribution, this is the most widely used way of asymptotics, is just to give you a closed form to work on. So in other words, if you can derive that for a statistic, then, and if you think the limiting distribution is a very good approximation, then what you can get out of it is that you can say, oh, basically, I just use that to get my confidence interval based on a statistic for the parameter, or I can convert my statistic into a p-value under my hypothesis testing. So these are the things you can do. And it will be useful if you just want to be fast, right? Because using limited distribution doesn't require any additional computation. Okay, yeah, thank you for the comment.
Thank you.
Yeah. All right. So now let's move on. So this is where we stopped last time, convergence in law. So the convergence in law is regarding, how to say, the most general, the easiest way to satisfy. In other words, we just want to use this, we want to obtain this result, xn converges in law to x. So in other words, if this happens, then the distribution of x is called the limiting distribution for xn. Okay, so let me just write here. Fx is the limiting distribution of xn, fxn. So in other words, you will use fx as the approximation if it's a nice form. And this Haley-Bray theorem is a foundation for obtaining the widely used theorem, which allow us to use convergence of characteristic function to prove convergence in law. And that's the result we use for deriving central limit theorem. So Haley-Bray is just the foundation of that. And as I said, basically the idea is to have equivalence between A and D. D means that for any function G that are bounded and measurable function such that the random limit x is in the continuity set of G with probability 1. So with this kind of G, general function class G, if we can prove that for all such G, then expectation of G applied to Xn converges to expectation of G applied to X, then we can have convergence in law. But to prove this thing, essentially B and C, the two statements are introduced in the middle. They are just smaller function classes for G. Like for B, you just consider all continuous functions that vanish outside the compact set. So they have compact domains. And for C, you consider all continuous bounded functions G. So in other words, you can show that B is a special case of D, D is a special case, so B is a special case of C, C is a special case of D. Okay, and then finally, you want to establish equivalence between A and D. So the proof idea is by a circular thing, in the circular way. You go from D to prove A, because A, you just need to show that the function is the CDF function, right? So you want to use that, and CDF function is a special case. So CDF function is a special case of G, basically. Or I should say it wrong. CDF function is a probability, and probability can be written as expectation of indicator function. And then the indicator function is a special function of G. So that's why if you have D, you can get A. But then from A to D, the equivalence, that is not easy. So that's why you go from A to B. So indicator function to continuous functions with the compact domain support, and B to C and C to D. So that's the whole idea of proving Hillenbrand. And the proof itself uses a lot of the techniques we use from the measure theory. All right, so continue. And let me see, this is the characteristic function definition, because we need this definition to be able to show that theorem where characteristic function convergence implies CD convergence along. Okay, so this is the characteristic function. So essentially, it can be defined for a random vector X, and its domain is also d-dimensional. Okay, the dimension is the same as the random vector dimension. So at a vector t, essentially the characteristic function is defined as exponential function of e, the exponential function, expectation of exponential function of this imaginary unit I times t inner product with x. So now you see both are d-dimensional vectors, their inner product is a scalar. So essentially characteristic function value is scalar. So you can see basically what it maps to is this. So and you know this Euler's formula, right? We can always write this exponential of some imaginary unit by the cosine and sine thing. So that's why you know this characteristic function, it actually maps from this to this interval. This is what its domain and what its range is. Okay, so the characteristic function is defined in this way, and using that, essentially, we can have this most important result. It's called Levy's continuity theorem. So, in other words, you can just prove the convergence, point-wise convergence of the characteristic function, then you can prove convergence along. And that's exactly what we use in proving central limit theorem. So recall that for the central limit theorem, what we have is Xn bar, the sample mean, converges in log, right, to some normal distribution. That's the thing. But here I'm skipping all the details here because you also need to consider the sample size n somewhere. You also need to consider the population mean somewhere. So I'm putting it here in the empty form just to maybe help you remember what you have learned before, but we'll show you the detailed result later. So just to make it surely, the limiting distribution on the right-hand side, we don't want it to change with n because it should be something stable. And anything related to n, related to your statistic, related to your sample, should go on the left-hand side. So therefore, I should say the exact form should be root m times x minus mu. You need to do this stabilization on the left-hand side, then the right-hand side won't be related to n. Okay, so to prove that, essentially, you just need to show the convergence of characteristic function. Okay, and I can say that the proof will follow Hillenbrand. So essentially, the first direction from left to right is a direct result of applying Hillenbrand from statement A to statement C. But backwards, right, going back is not easy because you want to prove that this right-hand side implies the Hillenbrand, one of the statements in Hillenbrand. Okay, so here we can show that for any G continuous validation outside compact set. So this is what we have for statement B. So you're just trying to show that with the convergence of characteristic function, then you can achieve statement B in Hillenbrand, and then based on Hillenbrand, you can go to the convergence in law. And the idea in this proof is also very interesting because basically we want to introduce the form of characteristic function. So using its definition, we want to introduce the form by basically introducing some Gaussian noise, like by adding this y sigma, which is itself Gaussian noise, independent of xn and x, we add it here. then we use those inequalities to help us basically go down here, expand the form. So essentially, this expectation of G applied now to xn plus y sigma, not xn alone, then can be written in this form. And we can somewhat introduce the characteristic function form. So the proof is technical, but I think it has some very interesting ideas. And also another take-home message is that Gaussian has a very easy to work with characteristic function. And also Gaussian is something very nice. So mathematically very nice. So that's why a lot of the theoretical statistical results are really related to Gaussian. Okay, so as I said, this time we will skip the proof, and also we use Fourier transform here. So we use Fourier transform here in the proof. Essentially, we basically need to go from this equation 5.1, which is about this expectation of G applied to xn plus y sigma, show its convergence. And this will be the expectation of G of x plus y sigma. So in other words, we're showing this convergence, we're showing this instead of showing the Hillenbrand, which is this. So even though this is what we want to prove, but we're actually proving this. And our hope is that by setting the sigma, the Gaussian noise magnitude to be very, very small, then having this essentially implies this. That's the idea. All right. So Hillenbrand and Levi's continuity theorem are what is important about convergence and law. Now we talk about law of large numbers. So this is something we all learn in introductory statistics, but here we just want to give you a little bit more about what it means. Okay, especially now you have learned the 4 modes of convergence. So this is just some notations, derivatives for vector value functions of a vector variable. So what does that mean? So this is what I mean. So basically, the function g is applied to a d-dimensional vector, and the output is a k-dimensional vector. So it maps from d dimensions to k dimensions. How do we derive a derivative for such a g function? Before we do that, we first look at this real valued function, f. So here, even though the input is still d-dimensional, vector input, but the output is one-dimensional. We get a scalar value output. So this is called real value function. So in this case, the derivative is written as a vector. And here in this class, we followed that Ferguson book by using this notation, putting a dot on top of f. And we use row vector for convention. So this is the derivative. And people also call this gradient, right? Gradient is the first order derivative of a real value function of a vector. Okay, so essentially you are taking the partial derivative of f against each dimension in the input. So 1 to d. So therefore, the derivative is a d-dimensional row vector for f. Okay, now g, moving forward to g. G is a k-dimensional output function, right? So we can write the output of G as k dimensions, G1 to Gk. So each one is like f. It inputs a d-dimensional vector, outputs a scalar. So therefore, when we say the derivative of G, it now becomes a matrix. So every row corresponds to one output dimension, and every row is what the output function's derivative as in f. So therefore, you see that we have d columns and we have k rows. So the k rows refer to the k output dimensions, and the d columns refer to the d input dimensions. It's a k by d matrix. Okay. And how about the second derivative? Second derivative for, let's look at the real value function first. So this is our f dot, right? We already get a vector. Now you want to take the second derivative. So it's like you're taking a derivative of this. And essentially we get a d by d matrix, okay? So this is the second derivative. And this is also called the Hessian matrix for this function f. And we put f double dot on top. Okay, so these are some results you should have learned from calculus, but now we're just showing you the matrix form, vector form. First one, chain rule. If you have F maps from RD to RS, D dimensions to S dimensions, G from RS to RK, then GH as the composite function, it's just G applied to Fx, so it maps from RD to RK. Then you have the chain rule. So Hx is just G, H dot x is G dot applied to Fx and F dot x. Okay, this is chain rule in calculus. Second thing, product rule, right? So if you have F d to k and G d to k, so both Fx and Gx are k-dimensional. So we can define Hx as their inner product, then Hx is one-dimensional. Then if we do H dot x, we would have Gx, so H dot x is what? It's d-dimensional. So we keep the dimension in mind. So it's actually Gx transform, which is what? Gx transform is 1 by k, okay? Because Gx is k-dimensional, 1 by k times F dot x, based on what we just said, it's k by d. So that's why here you get 1 by d. And that's the dimension you get for H dot. And plus the other way around, Fx transpose G dot x. So when we work with vectors and matrices, it's very important to keep checking the dimensions to make sure we're correct. Finally, mean value theorem. So this is what we use a lot in asymptotics for approximation. And this is just like Taylor expansion, right? So essentially, you look at f function value at x0 plus t, then you just approximate it by f function applied to x0 plus some term times t. So essentially, this term is the mean value. It's actually somewhere between x0 and x0 plus t, right? So in the middle of that, and you take the derivative of that. Derivative actually, the derivative is with respect to the argument of f. You apply that derivative to the mean value, the middle value, and you take integral over this line segment, I should say the line segment between x0 and x0 plus t. Okay, that's the mean value and times t. Okay, finally, Taylor's theorem. It is very similar to the mean value theorem, except that you go in one more term. So you basically include the first derivative, and then the second derivative. So if you apply Taylor theorem, Taylor expansion in this way, then once you do more expansion, then essentially you are getting a more accurate approximation. Okay, so these are the things we want to review for the mathematical notations. And before we talk about the law of large numbers, there's another thing we want to introduce. Two types of consistency. So in this language, when we say consistent estimators, we need to be more specific. So the weak consistency means convergence in probability. Strong consistency means convergence almost surely. So if you have the limit as your true parameter value theta, and xn just represents your estimator. So essentially, strong convergence means that in any realization, you know that your xn is close to theta for sure, right? In your realization. So you don't need to worry that your observed value for the estimator is an exception, is an outlier for strong consistency. But for weak consistency, it's possible what you get is an outlier. And only when you get many, many realizations of your estimator, you know that with high probability, your estimator is close to the true value. So in many, many of the statistics theory, we only have the weak consistency for us. and we don't actually have the strong consistency because it's very difficult to achieve, right? You don't allow for exceptions. How is that possible? Or in many cases, it's too strong to argue for that. Okay, but one example to take a look is this very interesting problem, which we'll see later. It's about what? It's using the order statistic maximum of your sample. Okay, x1 to x2 to xn, we define xn to be the maximum. And we want to use that as an estimator for this upper bound in your domain. So assuming that x1 to xn are independent and identically distributed IID from this uniform distribution with domain 0 to theta. So theta is the maximum of your domain, but we don't know it. We want to estimate it. Then the natural estimator is to take the maximum of your sample, right, xn. But how good is xn as an estimator? How good is it, right? So we can actually show that it is a weakly consistent estimator. So it satisfies the weak consistency. So to prove that, we just need to show xn converges to theta in probability. And we go back to the definition of convergence in probability. So for every positive epsilon, we calculate this violation probability. Since x1 to xn, they must all be positive, as this domain is from 0 to a positive theta. They must all be positive. So in other words, and also they must be all positive and they must all be under theta, right? Theta is the maximum. So therefore, this violation, xn minus theta absolute value, if you open it, it will become theta minus xn because we know xn is under theta. So therefore, theta over xn is, let me see. Yeah, basically we have this. Theta minus xn greater than epsilon. So therefore, I think there's a typo here. Then this should be xn less than theta minus epsilon, right? That should be what it is. And once you have that, then it basically implies that everything is under this. x1 to xn. Each of them is under theta minus epsilon. And then we can use the independence to get the joint probability. That's the basic idea for this proof. Okay, so that's it. Consistency, weak consistency, and strong consistency. And then another thing we want to talk about, now we have the convergence in probability. Now we can generalize our small o, big O in lecture 1 to this probability sense. In other words, here we are looking at random variable sequences instead of real number sequences in our lecture 1. So this is it. So now we can write small op. We write xn is small op of yn if this ratio goes to 0 in probability. Recall that we write real number sequence an is small o bn if an over bn is convergent to 0. That's what we have. But in that case, the convergence doesn't need to specify a mode because it's just real number convergence. Now it's random sequence. So we need to specify the mode and its convergence in probability. Okay, and specifically, if you just write small op1, this is very common. It is just a shorthand notation for a sequence of random variables convergent to 0 in probability. That's small op. Okay, next big op. So same idea. Previously, we just have the limit bounded, right? Now we will have the limit bounded with high probability. So essentially, you just apply this improbability, let me say, so basically you just apply this convergence in probability definition here. So you want to say that for every epsilon greater than 0, there exists an m and n. So n means that, okay, you're really far into your sequence. After this m, everything satisfied that they're bounded by m. So m is the bound, and n is the index you have in your sequence. And they all satisfy that bounded with high probability. So essentially, this big O P is useful when you just want to say that this ratio, xn/1 ratio, has some bounded behavior, limiting bound behavior. So as n goes large, they are within some bound with high probability. That's what you want to say. And this happens for every epsilon greater than 0. Okay, so that's the big OP, small OP and big OP. And we also can look at this bounded improbability measure. So it's for small OP1. Okay, that's a special case. Big OP1, special case. So we say that x1, x2 is bounded in probability if xn is big OP1. That is, for every epsilon greater than 0, there exists m and n such that the absolute value of xn is bounded by m with high probability. Okay, for all n greater than m, you have this happens with high probability. So you're just applying this concept of big OP to replace ym by 1. That's it. Okay, so now let's look at that maximum example again. We just look at it. x1 to x2 to xn, their IID from this uniform 0 to theta. We show the maximum converges to theta in probability already, right? Equivalently, we can also say that xn is theta plus small op1. That is, their difference is going down to 0 in probability. You can also relax this to say xn is theta plus big op1 because small op is included in big op, but this is less informative than saying small op. Okay, and we will show later that this statement, this one, small op1 here, can be more specific as big op 1 over m. It means that, yes, this term is going down to 0 in probability, and it's going down in the rate of 1 over m. So now you can specify, or at least the rate of 1 over m. Could be faster, but not slower. So you can give a more informative bound. All right. Any questions so far? So we just talked about small OP and big OP, and we introduced some notations on the derivatives. And consistency, we talked about that as well. So we convert consistency is convergence and probability. Strong consistency is convergence almost surely. All right. If there are no more questions, then we will move on to law of large numbers. So law of large numbers, very similar to our modes of convergence. Here we can have convergence in probability, convergence in quadratic mean, which is like the Rth convergence, Rth mean convergence with R equals 2, and strong convergence almost surely. So basically, we have the 3 stronger modes covered here. And you know what? As long as you convergence in probability, you have convergence in law, right? So that is already implied. Okay, so essentially law of large numbers is talking about the behaviors of sample mean. It says that as our sample size goes larger and larger, then our sample mean will get closer and closer to the population mean. And we have the 3 modes of convergence. All right, so I will skip the proof because, as we said, it's not easy, actually, especially for the strong law. If you are interested in learning it, there are some reference in the note you can refer to. Yes.
Professor Jessica, just a quick clarified question. What is the difference between the expectation bracket X and expectation without bracket X, like mu equal to EX? And
no, it's
yeah.
not bracket, it's absolute value.
Oh, I see.
Yeah, it's absolute value. Yeah, But we can always write bracket for the most formal way of writing, but we leave out the bracket just for simplicity. Yeah. Yeah, because it's possible you have expectation of x being 0, but expectation of absolute value x being infinity, right? Because if the distribution is symmetrical, even though it's too heavy-tailed that you don't have expectation of absolute value being finite, but you can still have expectation of x being finite, being 0, because you have cancellation of the positive and negative values. Does that make sense?
Yeah.
Okay. All right. Yeah, so for part B, let's look at the correct and mean proof, because this is very useful. So that's why I think it's worth talking about. So for this one, essentially, you want to show this going down to 0, right? This is our goal. And you can write it as this inner product. So we are talking about the vector form. So both x and bar and mu can be d-dimensional. So in this inner product form, we further spell out x and bar as the average of x1 to xn. So here for this one, we enumerate xi from 1 to n. For the second term, we enumerate xj from 1 to n. This is what we get. Okay, and we also use the IID. So this is based on the IID property, identically distributed. So then, because of IID, we can also go here. Because when I and j are not equal to each other, then we can just take expectation of each, right? Expectation of the product is equal to the product of independent expectations. So then we get zeros, cancellation. So we're only left with terms where I and j are equal. That's what we have. And this is essentially further reduced by IID. So every step uses IID because each xi is a copy of x. So we just need to keep the one copy. So we have n of that, then this n cancels with this denominator n. So we have this. And therefore, as long as you have this finite, a finite thing divided by n will go down to 0 as n goes to infinity. Okay, so this proof requires only that xi's are uncorrelated and have the same mean and covariance matrix. So same mean covariance matrix is important for us to go from here to here. It does not require they are independent or they're identically distributed. Essentially, I'm giving the stronger condition here, but essentially, if you want to relax the IID, you can make it weaker, right? You don't have to go as strong as IID, but I'm just saying if it's IID, then this follows naturally. Okay, so basically this expansion of statistic in terms of your sample, x1 to xn, and using identical distribution for simplification, this is very general and useful for proving consistency in statistical estimation problems. Okay, and this is something I also want to go over a little bit, the remark too, since we have not specific talk about this weak law, right? This is weak law of large numbers, and this corresponds to weak consistency for convergence and probability. For strong law, almost surely it corresponds to strong consistency for the strong consistency for estimators. So the part A, the weak law of large numbers says that if x1 to xn are IID random variables with finite first moment mu, this is it. So finite first moment mu and finite absolute expectation, then for every epsilon 0, we have this go down to 0 as n go to infinity. This is the definition of convergence and probability. And part B shows that this one goes down at rate 1 over n. Okay, it's here. Okay, because this is the rate we get from part B, 1 over n, and we can also use the Markov inequality or Chebyshev inequality to show that convergence in correct mean implies convergence in probability, the upper bound. So that's why we get the rate 1 over n. Actually, the rate of convergence for this to 0, actually, there's a typo. It should be bigger than epsilon. It's not just this. to 0 is typically exponential at a certain rate that depends on epsilon and the underlying distribution of x's. That is, I should add greater than epsilon here. This violation probability behaves asymptotically, actually in the exponential rate. So this rate is just an underestimate of the rate. We are just getting this rate, but it could be actually faster. So it's actually, we can actually show this. Okay, and actually to show the rate of convergence to 0 in terms of M is the domain of large deviation theory, or the one I just said, concentration inequality. So that will give you the rate. So here we're just saying convergence to 0 in probability, but we don't specify the rate. But you may have different estimators, they all convergence in probability to the parameter. But if their rate is different, then the one with the faster rate is considered to be better. That's the intuition here. Okay. And yeah. Okay. That's all. That's it. That's the law of convergence. So something we will also touch a little bit later in the class, but we will give you the foundation here, is this consistency of empirical distribution function. So this is interesting because essentially when we do the real, when we face a real sample, we never know the true distribution. It's always an assumption, right? Because we don't know what the true distribution the data come from. But we can obtain empirical distribution from just our sample x1 to xn, especially when your n is large. We can get an empirical distribution to be quite close to the true distribution, the true CDF function. So what is it? So the true CDF function, suppose that we have x1 to xn IID from the same distribution as x. Then the true CDF function is this, right? It's just the probability that big X is under less or equal than small x, and we call that f small x. That's the CDF function. But this is something we don't know, we don't observe. So what we can observe, and this is the non-parametric maximum likelihood estimate of f, is the sample distribution, or some people call it more commonly empirical distribution, which is defined as this. That is, you are basically estimating this probability by a proportion. So given a small x, you just count how many xi's are under the small x, and you divide that count by n. That's the proportion. And this proportion is our empirical CDF function. And we refer to this as f and x. Okay. So then natural question arises, that is, how good is this f and x as an estimator of fx? Okay, so because both are functions, right? Both can take the argument x and change with x, then their relationship can be more complicated because we can talk about their relationships like f and x and fx for a given fixed x. Or we can talk about their relationship across all values of small x, and that's different. First of all, if we fix x, it's simpler because we have the strong law of large numbers, almost sure convergence. That's very, very strong. We said it's not easy to achieve almost sure convergence, but for law of large numbers, we can achieve that, which is very good. And just to come back here, the only requirement is that we need to have the random variable distribution to be not so heavy-tailed. So the absolute value expectation is finite. That's the only assumption condition. All right. So for fixed x, strong law of large numbers implies that fn at this x converges almost surely to f at the same x, because we may consider this indicator function as IID random variables with mean fx. So therefore, the sample mean converges to the population mean. Okay, so therefore, this empirical CDF f and x is a strongly consistent estimator for fx for each x, for each small x. But we can see a stronger result, which is we can look at across all x, small x values in a uniform way. So the Glivenko-Cantani theorem states that the empirical distribution function converges uniformly, almost surely. Here the key word is uniformly, almost surely to the true distribution function. So it improves this result in two ways. First, the set of probability 1 on which the convergence takes place may be chosen to be independent of x. Okay, what does this mean? Second, the convergence is uniform in x. So in other words, basically we can have the convergence that happens, let's just say, I will give one intuitive way to understand it, is that previously, even though we know f and x converges to fx almost surely, but the convergence rate could be very, very different for different x, right? It could be somewhat slow for some x, but faster for some x. And then we can not really coordinate the convergence. But for this uniform convergence, they are coordinated. So essentially, it means that we can basically find some band to basically put our f and x in, and that band can happen for all x. Instead of saying, okay, we may have like a divergent band for some x, because if the convergence is too slow, and that is something we may have for the pointwise convergence, but not uniform convergence. Let's look at one example to help you understand if this is something not so familiar to you. Pointwise convergence doesn't imply uniform convergence. So here we just write the function, okay? Just write some function sequence for understanding. So that is f and x is x squared over m plus x, and fx is x. Okay, so if you have this, and we want to say this is the limit of that. So yes, for a fixed x, then you let n go to infinity, then you will have this go down to 0 as n go to infinity for any fixed x, right? So you do have pointwise convergence. But now if you let x change, and x can be anywhere, right? Then if you take the soup of this, and it's that. So basically soup of difference is soup of this. Since x squared can be any value, we can take it as n squared. Then you will have divergence. So the soup x of the difference doesn't converge, but the pointwise difference given the fixed x converge. Does that make sense? So you see basically the difference between f and x and fx, the convergence rate depend on x value itself. So that's why you don't have the same rate. So in this case, you do have pointwise convergence, but you don't have uniform convergence. So uniform convergence is a stronger result. So in other words, when we say, let me just try to clarify a little bit. So for pointwise convergence, you only need to say fixed x, and you have f and x minus fx go down to 0. That's it. But for uniform convergence, you're not fixing x. You're considering all possible x. So you need to look at the supreme across all values of x of this difference. You need a soup to go down to 0. So it's a much stronger requirement. Okay. But this Glivenko-Cantali theorem actually gave us the uniform convergence of empirical CDF function converges to the true CDF function. We have the uniform convergence happens with probability 1, which is very nice. So essentially, another way to write this is soup x f n x minus fx. And please note that this is random. The randomness comes from the fact that fn is a random function because this function depends on x1 to xn. But fx is not a random function. So coming back here, fx is just a probability, not random, but f and x is just an operation on x1 to xn, and x1 to xn are random, so f and x is random. Okay, it's a random function. So therefore, this is a random quantity. If we want to say it converges to 0, we need to specify the mode. And here, the mode is almost surely. So that's what the Glivenko-Cattani theorem is saying. All right, so it gives us a very strong result for using the empirical CDF function because it's a nice property about empirical CDF function. That's it. But why can we get a strong result? Uniform convergence almost surely. The fact in the proof, even though I'm not going to go into detail, but it lies in the fact that CDF function is actually bounded. That's the reason. Because for every CDF function, it ranges from 0 to 1. So its range is bounded. Because of that, then here the uniform convergence can be obtained. Because if you look at this counter example here, the reason we cannot have uniform convergence is that both functions are basically exploding, right? So you see that this function value increases as x increases, and also this function, and their difference, which is x squared over 2, also increases as x increases. So it's not bounded. That's the reason. But here we have bounded. Both are between 0 and 1. Okay. That's all. So we will probably go back to using this result again, Glivenko-Cattani theorem, when we want to give you a light touch on the empirical process, which is also something quite useful in many theoretical studies about if you want to do some theory about your statistics, then you need that. All right, so that concludes what I want to talk about for the law of large numbers. So we went quite quickly, quite fast. We talk about different modes of consistency, in particular, strong consistency based on almost sure convergence, weak consistency based on convergence and probability. We talk about small OP, big OP, which generalize small o, big O in the sense of convergence in probability. Yeah, and also we talk about the law of large numbers, right? We talk about law of large numbers. Strong law is almost sure, and weak law is convergence in probability. We also have the convergence in quadratic mean for the law of large numbers. And finally, we talk about this Glivenko-Cattani theorem is regarding empirical CDF function convergence to the true CDF function. For the pointwise convergence, we just need strong law of large numbers. But for the Glivenko-Cattani, we talk about the uniform convergence almost surely. Okay. Any questions before we continue? So because this is basically what I want to cover in lecture 3, and I can pause here and we can record the second one if you still are available. Okay.